All right, in this video, we're going to be looking at vectors. So there are two types of physical quantities that we deal with. The first are called scalars. A scalar has a magnitude, or how much, and a unit associated with it. Some examples of scalar quantities are temperature, time, mass, and speed. So for example, the room might have a temperature of 72 degrees Fahrenheit. So it has a magnitude, the 72, and a unit, the degrees Fahrenheit. Time is also a scalar quantity. It has a magnitude and a unit. Same with mass and speed. These are all examples of scalars. The other type are called vectors. A vector has a magnitude, or a scalar component, so it has a magnitude in its unit, but it also has a spatial direction. That's also important. Some examples of vector quantities are force, displacement, velocity, and acceleration. These are all vector quantities. They all have a spatial direction associated with them. So for example, if I have a desk sitting in the room and I want to move the desk, well, I could apply a force, such as a push or a pull. I could push the desk and cause it to move. But it matters not only how hard I push, but the direction that I push is also important. So if I wanted to move the desk across the floor and I push straight down on the desk, it doesn't matter how hard I push, that desk is not going to move across the floor. Now if I get down and I push horizontally, then I can move the desk across the floor. If I push at an angle, I could probably move it, but I would have to push harder than if I pushed horizontally. So the direction that I push is also important. So it's not only how hard I push, but the direction. So we're going to learn how to deal with vectors in this and deal with the directions in this video. So in many problems, we have to combine vectors. So when we're adding vectors, we have to consider their spatial directions. We can't just simply add the magnitudes. So we're going to learn how to do that now. All right, we can add vectors graphically, and this is called the head-to-tail method. So I have a coordinate system, and I first draw in my vector A, shown in red. So I start at the origin, and I draw vector A. Then if I want to add vector B to vector A, I draw in vector B starting at the arrowhead end of A and draw in vector B. Then vector C, which is the resultant of A plus B, I go from the origin at the beginning of A and draw it up to the arrowhead of B. So we can see then that vector C is equal to vector A plus vector B. So now vector C includes both the magnitudes and the directions of vectors A and B. So this is the head-to-tail method. So we draw on the first vector, vector A, and then at the end of vector A, I now draw vector B, and then the resultant, which is vector C, equals to A plus B, starts at the beginning of A and goes to the end of B. Now in the figure on the right, this is what happens if A is all in the X direction and B is all in the Y direction. Notice it gives me a right triangle, and vector C, which is equal to A plus B, is the hypotenuse of that triangle. All right, this illustration shows that the order of the operation doesn't matter. So I can either do vector A plus B or vector B plus A, and I get the same resultant. So here I've drawn in vector A in red, and I've also drawn in vector B in green, both of them starting at the origin. Now if I project vector A upward to where it is in the dotted line position, and I project vector B to the right, where it's shown in its dotted line position, I can see that the resultant vector C can be equal to A plus B, or it's also equal to vector B plus vector A. So even though the vector A in the dotted line shown at the top doesn't start at the origin, it has the same length, which is the magnitude, and it has the same direction. So the vector is equivalent, even though it doesn't start at the origin. It's still the same vector because it has the same length and the same direction. All right, also notice that this forms a parallelogram. So this is often called the parallelogram method of adding vectors. So if I want to add two vectors, I just make a parallelogram with the two vectors as the legs of the parallelogram, and then the resultant, or the sum of those two vectors, is the diagonal of the parallelogram. Okay. Another thing you should notice here is that the greatest that the resultant can be is the greatest magnitude that the resultant can have is when vectors A and B point in the same direction, and the smallest the resultant can be is when A and B point in opposite directions. We can also see that if a vector sum is going to be equal to 0, then they have to point in opposite directions and be the same length. Right? So the only way a sum of two vectors can be 0 is if they have the same length and they point in opposite directions. Okay, what if I want to subtract vectors? Well, subtracting a vector is the same as adding the negative of the vector. And the negative of the vector just simply reverses its direction. It'll have the same length, it just reverses the direction of the arrow. So in this illustration here, I have drawn in vector A starting at the origin, and then I have drawn in vector B in green, and we see the resultant in blue of vector B plus vector A. Now, if I want to do vector A minus vector B, I just simply reverse the direction of vector B, and that becomes vector negative B or minus B. And then the resultant of A minus B is shown there. So adding the negative of a vector is the same as subtracting the vectors. And so that resultant is shown here. All right, I can multiply a vector by a scalar, and all that does is change its length. It does not change its direction. If I multiply by a negative scalar, it reverses the direction. With same orientation, just reverses the arrow direction. All right, we can also use what are called unit vectors, and that's shown in this illustration. So on the left side, I have vector A shown. So it has its magnitude, the length of the vector, and it has a direction. Well, there's a little vector next to it. It has a length of 1 unit, whatever unit system we're in. And so I have a small a with a little caret above it, and it's read as a hat. So a hat is called a unit vector. It carries the direction information. So it has a length of 1 unit, whatever system we're in. And so then if I just multiply a hat by the scalar component of the vector, then I get vector A. So vector A is equal to its length, A, and that's not bolded, times the unit vector A hat. And so that gives me the vector information. And then on the right, I just reverse the direction. So the negative vector A equals the negative of vector A length times A hat. Or I could also write it as the length of vector A times a negative A hat. And so that reverses the direction. So we will talk more about unit vectors a little bit later in this video. All right, so you can see that adding vectors graphically does not have a very high degree of precision. So if we wanted to add vectors graphically, we have to use a ruler and a protractor and be very careful how we make our drawings. But there's another way that we can use to add vectors that's much more practical, and this is called using vectors in component form. So in component form, we take advantage of right-angle trigonometry. We make our vector the hypotenuse of a right triangle. So we draw the vector in, and then we construct x and y components which form the legs of the right triangle. So the vector becomes the hypotenuse, the x component and the y component become the legs of the right triangle. Now we draw a vector and angles are measured counterclockwise from the positive x-axis. And so we call that angle theta. So then the x component is equal to the magnitude of the vector A times the cosine of theta, and then the y component is the magnitude of the vector times the sine of theta. And these follow directly from the definitions of sine and cosine. So if you're a little rusty on your trigonometry, I suggest that you look at a tutorial on right-angle trigonometry. I'm sure there are numerous YouTube videos and websites that have right-angle trigonometry tutorials. So you may want to brush up on that if you're not very comfortable with right-angle trigonometry. All right, so now when we have the x and y components of the vector, and we want to combine different vectors, we can just add up all the x components of the various vectors, and that will give us the x component of the resultant, and then add up all the y components together, and that gives us the y component of the resultant. And we'll look at some graphs here to show how that works. All right, here, this is an illustration that shows how adding vectors in component form works. So on the left side, I have vector A drawn in and vector B drawn in the head to tail method, and we can see vector C is equal to the sum of A plus B. All right, so now I've broken vector A into x and y components. So notice I form vector A is the hypotenuse of a right triangle, and AX and AY are the legs of that right triangle. Similarly, for vector B, I have BX and BY are the legs of the right triangle with B as the hypotenuse. So now when I want to add vector A and B, I simply add vector AX component and the BX component together, and that gives me the resultant vector C in its X component. And then to get the Y component of vector C, I just add the Y component of A and the Y component of B. So you can see how that works. So the resultant vector, the X component, is simply AX plus BX, and the Y component of the resultant vector C is AY plus BY. So now I have the X and Y components of vector C. And then if I want to find the length or the magnitude of vector C, I can just apply the Pythagorean theorem, cx squared plus cy squared, and then take the square root of that, and that will give me the length of vector C. All right, if I have a vector in component form, I can also express it in a form that's called the magnitude angle form. So I can find the magnitude of the vector by simply using the Pythagorean theorem. So the length of the vector, or the magnitude of the vector, which is the length, is just the square root of the sum of the squares of the two legs. So the length of A here is equal to the square root of the x component squared plus the y component squared. Then if I want to get the angle, I can take the inverse tangent of the y component over the x component. So remember, tangent is opposite over adjacent, right? Now notice I have absolute value signs on the inverse tangent. So we have to be careful when we use the inverse tangent function on our calculators, because our calculator will not always give us the correct answer, and we'll illustrate that in the next picture. All right, so why do we use the absolute value signs when we apply the inverse tangent function? Well, that's because of the nature of the calculators that we use. When I use the inverse trig function on a calculator, the three graphs on the right of the slide here show the range of angles that you get from most calculators when you apply the inverse trig functions. So for the inverse sine function, I'll get an angle between minus 90 degrees and plus 90 degrees. For the inverse cosine function, I get between 0 and 180. And for the inverse tangent, I get an angle between minus 90 and plus 90. So the answer that you get from your calculator when you do the inverse trig function to get your angle theta may not give you the correct angle, depending on what quadrant of the coordinate system that your vector lies. And so we'll go over some of those details in the following slides. Okay, so here is an example. We have vector A. Notice the arrow on the top of the letter A, indicating it's a vector. And the components Vector A is given as minus 5.2 I hat plus 3.0 j hat. I hat is a unit vector that points in the x direction. J hat is a unit vector that points in the y direction. And if we have a component in the z direction, that would be k hat. So I hat, j hat, and k hat are unit vectors that point in the x, y, and z directions respectively. So vector A, then, we see that the x component is negative 5.2 and the y component is 3.0. So where is this vector going to be in the coordinate system? Well, since the x component is negative, the y component is positive, we're going to be in the second coordinate, or second quadrant of the Cartesian coordinate system. Now, I can express the magnitude by applying the Pythagorean theorem. So the length of a squared equals ax squared plus ay squared. So a then is the square root of 5.2 squared plus 3.0 squared, and that gives me 6.0. So that vector A has a length of 6. Now to get the angle, I'm going to take the inverse tangent of the y component over the x component. But I'm going to use the absolute value, so I ignore the negative sign on the 5.2. Okay, so what happens if I don't ignore the negative sign on the 5.2? I just take the inverse tangent of the y component 3 divided by the x component negative 5.2. And what do I get for my angle? Well, my calculator tells me it's negative 30 degrees. But notice where is negative 30 degrees. So the convention is to go clockwise from the positive x-axis. Well, negative 30 then would be 30 degrees below the x-axis, and that would tell me that the vector should be in the fourth quadrant. But when I look at the components, I see the vector has to be in the second quadrant, not the fourth quadrant. So negative 30 degrees is not the correct angle for my vector. So this is why we ignore those minus signs when we do the inverse trig function. The next slide will illustrate what the correct angle should be. Alright, so I ignore the negative sign on the 5.2 and I find the inverse tangent of 3 over 5.2, and that tells me plus 30 degrees. Now looking at the components, I see that vector A lies in the second quadrant. So that means my vector is going to be 30 degrees above the negative x-axis. Right. So now I have my vector in magnitude angle form. I know the magnitude of 6 and the direction is going to be 30 degrees above the negative x-axis. Now I could leave it at that, but the convention is to reference angles counterclockwise from the positive x-axis. So to get the actual angle from the positive x-axis, I would take 180 degrees and subtract 30 from that to get to reference it from the positive x-axis. So then, following convention, I know my vector point is in the second quadrant and is 30 degrees above the negative x-axis, so I take 180 minus 30 and I get 150. So now in the bottom right of the slide, we have the vector written in magnitude angle form. So we have it written like an ordered pair, where the first number is the magnitude, the second one is the angle of the vector counterclockwise from the positive x-axis. So my vector A has a magnitude of 6 and it's at an angle of 150 degrees. So this slide just shows the 4 quadrants. So we have my xy coordinate system here. The upper right quadrant is quadrant 1. The upper left is quadrant 2. The lower left is quadrant 3, and the lower right is quadrant 4. So in quadrant 1, both x and y are positive. In quadrant 2, x is negative, y is positive. In quadrant 3, x and y are both negative. And in quadrant 4, x is positive and y is negative. So by looking at the components of the vector, you can tell immediately which quadrant the vector lies in. And now it's easy to find the angles using the inverse trig function of the positive values. All right, we're going to do an example here. We have three vectors, v1, v2, and v3 in magnitude angle form. We want to find the sum of these vectors. So first we're going to express our answer in component form, and then second, part B, we're going to express the answer in magnitude angle form. Now notice the vectors were all given in magnitude angle form. We cannot add them directly when they are in magnitude angle form. We have to break them into components. So the first step is we'll have to find the x and y components of each of these three vectors. So the first step, we want to find the x and y components of each vector. And so we do like we illustrated in a previous slide. You take the magnitude of the vector times the cosine of the angle to get the x component, and the magnitude of the vector times the sine of the angle to get the y component. The magnitude of a vector is always positive. So vectors always have a positive magnitude. Any negative sign is part of the direction. Right, so here I have the vector components for the three vectors. So in the first column we have the x components of vectors 1, 2, and 3. So v1 is x is v1 cosine of 45, which is 3.2. v2x is v2 cosine of 90 degrees, which is 0. And v3x is v3 cosine of 210 degrees, which is negative 7.8. v1y is v1 sine of 45 degrees, which is 3.2. v2y is v2 sine of 90 degrees, which is 5. And v3y is v3 sine of 210 degrees, which is negative 4.5. All right, so now to get the resultant, I sum up all the x components to get the x component of the resultant, and then sum up the y components to get the y component of the resultant. Right, so here I have the vector in component form. So when I add up the x components, 3.2 plus 0 minus 7.8 gives me negative 4.6. So I have my vector v, then the resultant is negative 4.6 I hat. Then on the y components, I have 3.2 plus 5.0 minus 4.5, and that gives me 3.7. So I have 3.7 j hat for the y component. So my vector v now in component form is negative 4.6 I hat plus 3.7 j hat. So that's the answer for part A. For part B, we want to find the vector in magnitude angle form. So to get the magnitude, I apply the Pythagorean theorem. So it's the x component squared plus the y component squared. Sum those together and take the square root. So negative 4.6 squared plus 3.7 squared, and then square root gives me 5.9. To get the angle, I take the inverse tangent of the y component over the x component, ignoring the negative signs. So the inverse tangent of 3.7 over 4.6 gives me 39 degrees. Now, looking at the vector components, I see the x component is negative, the y component is positive, so it lies in the second quadrant, and the 39 degrees is then going to be above the negative x-axis. So my vector has a magnitude of 5.9 and it points in a direction 39 degrees above the negative x-axis. So to reference it from the positive x-axis, I take 180 degrees minus 39 and I get 141 degrees. So the answer for part B, my vector and magnitude angle form, is 5.9 at 141 degrees. So that's shown in the lower right of the slide. Here's another example. I have vectors A and B are given. Vector A is given in magnitude angle form and vector B is in components. So the question says first, sketch each one, and then part B, we want to find vector C such that A plus B plus C equals vector D, where vector D equals 6.0 j hat. All right, so how are we going to do this? Well, first of all, we're going to do part A. So we want to sketch the two vectors A and B. All right, now here I've drawn a sketch of the vectors. And in a sketch, they don't necessarily have to be to scale, but I tried to sketch them as best as I could. So we see the vector A has an angle of negative 45 degrees. That means it lies below 45 degrees below the positive x-axis, and it has a length of 8 units. Vector B has both x and y components are positive, so it lies in the first quadrant, and that's shown in the illustration below. So that illustration is a sketch of both vectors A and B. Now we want to do part B. That will be in the next slide. So for part B, we want to find a vector C such that when I add A, B, and C together, I get another vector D, where D is equal to 6.0 j hat. Well, notice vector D only has a y component. There's no x component. That means ax plus bx plus cx must be equal to 0, since vector D does not have an x component. Then that tells me that C, x component, has to be the negative of ax plus bx. So that easily gives me the x component of vector C. And then I also know that the y components of A plus B plus C will equal to 6, since 6 is the y component of D. So the first part, let's find Cx. So I know Cx has to be the negative of the sum of Ax plus Bx. Well, Ax is A cosine 45 degrees, which is 8 times cosine of 45, which is 5.7. And Bx is just the j part, so I have, the I hat part, which is 2.0. So Cx then is going to be 5.7 plus 2.0, which is 7.7, and then I take the negative of that, so the Cx is negative 7.7. So I've got the x component of C. All right, so now I want to find the y component of vector C. So I know that ay plus by plus cy equals dy, which is 6. So cy is going to be dy minus the sum of ay and by. Well, ay is 8 times the sine of negative 45 degrees, which is negative 5.7. And by is equal to 4, and dy is equal to 6. So then cy is 6 minus negative 5.7 and minus 4.0, which gives us 7.7. So now I've got the x and y components of vector C. So now I can write the answer vector C in its component form. So vector C is negative 7.7 I hat plus 7.7 j hat. Okay, so we have vector C in component form. That's the negative 7.7 I hat plus 7.7 j hat. Now let's find it in magnitude angle form. So we apply the Pythagorean theorem. The magnitude of C, then I take negative 7.7 squared plus 7.7 squared, and then the square root of that, I get 11 for the length of C. And then the angle theta then is the inverse tangent of 7.7 over 7.7, which of course is 45 degrees. But I know that the x component of C is negative and the y component is positive. So that means it's in the second quadrant. So that 45 degrees, when I do the inverse tangent function, is 45 degrees above the negative x-axis. All right, then to express vector C in magnitude angle form, I already have the magnitude 11, and so the angle we saw was 45 degrees above the negative x-axis, so I take 180 minus 45, and the angle then is 135 degrees. So now we have vector C in both component form and magnitude angle form, which is 11 at 135 degrees. All right, so that's the end of these examples in the illustrations on adding vectors. So if you don't feel comfortable about this yet, just try a few problems yourself, and with a little bit of practice, it becomes automatic. All right, so future vectors now, we're going to look at motion in 2 to 3 dimensions, and we'll also look at relative motion, where we'll actually have to add some vectors. Hi, Dr. C here. Thanks for viewing this video, and please help support this channel and subscribe. Also, please leave your comments, questions, or suggestions, and I thank you for your support of this channel. I've also included a link to the next video in this series.